a path in the plane which starts at the origin, and so just natural thing. So you start at the origin, and at each step you are allowed to either go north by 1 unit or east by 1 unit. So it's a sequence of north and east steps which will sort of, a finite path of this kind will be called a lattice path. So this is the object that we will want to model. Okay. So the idea is to try and write a class which will model lattice paths and the various natural operations that you might want to do with them. So let's begin. So the first thing that we want to do is to try and so I'll say class lattice path. So the first thing is we will need to figure out how you will initialize such an object. So an object of this class is just going to be it's going to be a lattice path, something of this kind. So the question is what initial input will you give? You make it a little bigger. Fine. Okay. So the thing is we will need to make some choice on what initial data to give, how to describe a lattice path. So let's do it by giving it a sequence of n's and e's. Okay. So just like what I said, north and east. So I will call this so the initialization variable, let's call it steps. So which will sort of tell you what the sequence of north and east steps are. Okay. So what variables will we want? So let's say self dot, so again let me just call it steps, will be this thing called steps. Okay. So when I initialize this guy, what I will want to do is to sort of say, okay, let me also pull up a Python. So there's a Python interpreter. So let us Python. So exec file. .py. So what I will want is to call, so I will want to say something like L equals lattice path of a sequence a list whose elements are all n's and e's. So for example, I will say first go north, then go east, and so on. So this is sort of my what I have in mind. Okay, already a problem. Sorry, I missed name. Lattice path is not defined. What was that? Maybe I didn't save the file. Yes.
You return something?
No, but I have not. No, I just forgot to save the file. Now it's okay, right? So L is lattice path. So what am I doing? I am going to initialize it with just one attribute called steps, which will just keep track of the steps. So for example, if I say L dot steps, it's now going to something is wrong again.
It's without the brackets.
Yes, indeed. Thank you. Great. So L dot steps is just the set of the list that I given it, right? North and east. Okay, great. So that's the thing that I will want to do. Now, of course, so let's also use what we learnt about error handling and so on last time. So suppose the user inputs something which is not one of these two letters. If you input some garbage, you will want to complain right there. So I don't know, what should we say? So how should we catch a value error? We want steps to be a list, all of whose entries are n's or e's, right? So what should we do? How should one? So I guess there are various ways of doing it. Maybe the simplest thing is for I in steps, right? For I in steps, if I not equal to n and I not equal to and no, and, right? What am I doing? I am saying it's not n and not e, which means it's I mean negation will make it and, right? It's not n and not e. Then you complain. Raise value error.
Actually, is there any reason you would like them to be separate strings and not just one string together? Because after all, you can iterate over.
Right. Yeah, you can. You're right.
And in fact, that same checking code will work.
I guess the same code will work. You're right. So in essence, one could just. So what Damri is saying is you can think of it as
Any and
such this.
I think that should work.
Yeah, that should work completely. There's no problem. Strings and lists of individual characters are really the same thing. I'm just choosing it so that more of the list methods. I just want to. I guess all of them will probably work for lists as well. So in essence the same. I guess I'm just psychologically more attached to lists in some sense. So I'm just using lists for. So in fact, if you are like me, you could do the following. So there's the list function which just converts. So I mean, it's not even called the entire thing. If you have a string and you would rather think of it as a list, it seems like Python gives you this. It has I mean, all these iterables many of them have these list functions which will convert it into a list. The individual entries will become part of the list. So maybe I will henceforth just do this. So I'm really calling it as a list, but typing is much easier. I'm just calling it as a string. I mean, typing it as a string. Okay, so we raise an error in case there is a problem, right? So let's try this. Did I save the file? Let me exec file. Now we'll call it with some junk to make sure it's right. So it's raising an error because I had a k in it. So at least this is a basic setup. We've gotten an init method. So the next question is, what would you want to do with lattice paths? What are the next few things you would want to do? One thing is, of course, you would want to know the endpoint, right? Where does the thing end? So how should one determine what the endpoint of a lattice path is? So let's try and do that. So def endpoint of self, comma, no, just endpoint of self, right? Given the fellow, I know the thing. So we'll just do it in increasing order of sophistication. So Ambri's already said the most sophisticated version that one can do. So there are several obvious things you can do, right? So okay, what should you do? You must count the number of e's and n's. At the end of the day, that's all there is. Number of e's is the x coordinate, the number of n's is the y coordinate in that list. That's all there is to it.
Return that pair, the last.
You want to return the total number of e's and the total number of n's, essentially, right? So the most unsophisticated, naive code would be to run through the entire thing. So for I in self dot steps, so you run through the entire list of steps, and each time you find so let's maybe initialize x and y. So you say x equal to y equal to 0. So both are initialized to 0, and x is going to be, so if I is e, each time you find an east, you increment x equals x plus 1 or x plus equals 1, and else, since we have already raised errors in case you have neither of these, else y equals y plus 1. If it's not an east, it must be a north, right? Because we have ensured that. And then you return, so as you said, finally you return x comma y. Right? So this would be the natural thing to do. So for example, we say L is lattice path whatever, N, E, and E. For example, there are 3 E's and 2 N's, and now we'll say, oh, I have to.
So I'm not sure which is faster, but another possibility is to say self dot return. It's certainly your keystroke. Return, what is it called? Sequence. Is it? What is the
Steps.
Return steps dot count n, comma steps dot count.
Yes, absolutely. So that's the other thing. So what Amri just said is what's called a list method. So if you have a list, you have various things you can do with them. Okay, so that's the next thing here. So I just have the Python documentation. It says more on lists. So this is section 5, the tutorial, I think. So it says the list data type has some more methods. So here are some of the things you can do with list. So we've already seen some of these. Append and extend, we've already seen. So there's insert I comma x, which allows you to insert an element in the ith position of a list. Remove, which will remove, so remove of x will remove the first item whose value is x. Okay, and then there is pop, there is index, which could also be a useful thing in general. You have a list and you want to find the index of the first item whose value is x. But the one that is relevant to us is something called count. List.count of x will return the number of times x appears in the list. So this is something which is potentially very, very useful in many situations. So let's write another version of this. We'll say define endpoint 1 to be another implementation of this guy, where you just say, well, you can just quickly say what you want. Return self.steps is the list, and you say count of e, comma self.steps. So notice self.steps is already a list now, and dot count just means you're taking the method that acts on it.
So I wonder which is faster. You also showed me the first one is probably faster.
No, I think I don't know, at least somewhere in the Python documentation it says that you always use inbuilt functions or inbuilt methods,
the
right?
The second one is kind of counting through the list again. So when you do e,
so
maybe
I see.
It's better to have, in fact, right at the very beginning an attribute called length.
Absolutely.
Of self.
So let's just do that. So let's also keep track of the length of the path. So self.length is the length of, say the same thing.
Then you can just the second one can be.
You say self.length.
But then you need to store the first one.
Yes, absolutely. So you could do that, I guess. So what I guess suggesting is say x equals this, and then return x comma self.length minus x, right? So you say x equals this, then you return x and self.length minus x. Yeah?
You can do the same also for the previous one.
You can do the same for the?
Previous one.
The previous one,
No.
you are computing the length at the same time as you are.
Right. Yes,
So
indeed.
it seems to be faster in some sense, but I mean, I guess inbuilt functions run faster.
In the first one also you can avoid
Length minus this, you mean? Yeah, you could do that, yes. You could avoid the else statement.
just count all the e's.
Just count the e's and just say this. Okay.
But
Okay.
there is one advantage of the endpoint that it not the input not necessarily to be the list. It will also work on string.
This will work on
Everything
that also.
here will work for string.
Yeah.
Because count is
We should just check.
It will work for strings.
It should work. Pretty much anything you do with lists should work for string. So we just give something. Q is this, and you say q dot count of some character. So
You
it
can
works.
even give a substring in fact.
So these things work without. I guess lists and strings more or less are equivalent in many ways. So all these list methods will work for strings. Okay, so this is sort of a slicker way of getting there. Now, just to demonstrate, so we'll also do it in a slightly more lame fashion to demonstrate the use of two other things called filter and map. Okay, so there's another thing called filter which does the following. So it's again something. It's a function in some sense which acts on a list. Okay, so there are a couple of there are three of these, I think. So they're called filter, map, and reduce. So filter is the one that we look at. So what does filter do? Its input is some function. So so I mean I will just type the syntax. So the filter does the following. It has two arguments. One of them is a function and the other is the list. Okay. So what it does, filter is a way of producing a sublist. Okay. From the original list, you want to produce a subset or a sublist which only consists of those elements for which a function acting on them is true.
Can you make the font a little bigger, because I'm not sure it will be visible on the when it's recorded.
Okay. Is better? Oh, I guess I only did it on the Emacs. Sorry. This is okay, right? Maybe just once more. Okay. So the filter basically acts like this. It's a function which will act on the list elements, which should act on the list elements and the list itself. So what it will do is it will take element by element and then only determine the ones where it's true and collect them into a sublist. So for example here, so I mean this is a somewhat lamer thing, but it's applicable in a far wider set of situations. So let's do another implementation of endpoint. we will take a function which returns true on east, okay, and false on north, for example. So this also demonstrates another aspect. Within a method, you can define a helper function, for example. So here I will need this function f in order to pass to the filter. So I will define a function called f, which does the following. It takes an input x, and if x is e, or rather it returns x equals e. So it returns true if x is e and returns false if x is not e. Okay, so this is a function f. And now here's what you can do to produce a subsequence of the original list. So I have I take this function f and I apply it to the list self.steps, right. So self.steps was a sequence of n's and e's. What this will now do is it will apply this function f to each of the entries, and it will only pull out the ones on which it is true. Okay, so which is, for example, here it's true only if it is east, and this is now a sublist consisting of all the easts, right. So for example, let's do this. Let's for now just say return this and see what it gives us. So oops. File L is lattice path of this, and suppose I say L dot endpoint 2, it gave me only the 3 E's, right. It filtered the list and only pulled out the ones which matched, which had true on the function. So now what you have to do is just figure out the length of this sublist, right. So that's the x coordinate. So you return the length of this sublist, or as usual we'll do the same thing. X equals this, x equals this, and return the same thing as here. This is okay, so that's another way of doing this using the filter command, but as I said, here it's somewhat a lamer thing. So this brings us to another thing called lambda functions, which I think again maybe were talked about briefly by one or the other person, right? Maybe I forget who. Okay, Carl Dieter probably talked about lambda functions a little bit. So okay, so the point here is we had this little helper function f of x, but it's more or less just a one-line definition, right? It's a trivial definition. X, take input x and return the truth value of x equals e. So if you don't really want to have that as a separate function, what one can do is sort of just define it sort of on the fly, right where you need it, by just saying, so for example, so let's just do the same thing without explicitly defining this function. So you say filter, and then the function f is now replaced by its definition in place. So the syntax is, you say, instead of defining it separately, lambda is a keyword there. It takes input as x and you say what the output is. It's a truth value of this statement. Okay. So lambda x colon x equals e is already a function definition. It's the same as this function f of x, and then the same thing. So now this will do pretty much the same thing as
I think you can even define a function using f equals lambda, right?
I guess you can. Can you? It works?
Seems to work.
Okay. Okay, so you can even define a function like that. Just if it has a one-line definition, then this is a thing to do. If you're doing more complicated things, of course, then it's harder. Okay, so this is just to demonstrate lambda functions. Now, fine. So we have done enough with the endpoint. Now let's do something more with lattice paths. Okay, so what do I want? What more do I want to do with a lattice path? One thing I might want to do is to figure out whether it's a Dyke path or not. So let's try and write a method called isDyke. Okay, now what's the definition of a Dyke path? A Dyke path has two properties. Number one, it starts at 0, 0 and lands up at AA. It must land up on the diagonal, okay, the line y equals x, and such a way that it always stays, I mean you can choose either thing, it always stays below the diagonal, let's say. Okay, it's a path starting at the origin, ending at a comma a for some a, in such a way that it never goes above the diagonal, it always stays under the line. Okay, so that's the definition of a dike path. So let's try and figure out, given a lattice path, is it a dike path or not? Okay, so I want to write a method which will do this. So how does one figure out if something is a dike path? What should we do?
You should check each endpoint and
Yes.
but it may be better to write it again, like iterate through the path.
Yeah, so you need to keep checking the, at every endpoint you must see whether, so you need to scan it, you need to look at every subsequence, right? The subsequences will give you the various endpoints. So you do east, east, north, whatever. So the number of easts that you hit at any point should be greater than or equal to the number of norths. So in every subsequence, the number of e's should be more than the number of n's, right? For every subsequence of this list, the number of e's in that subsequence, for every initial subsequence of this list, the number of e's in that list must be more than or greater than equal to the number of n's. If that happens, then you are always going to stay below the diagonal. X is greater than equal to y for every endpoint of the diagonal. Okay, so that's the thing that we will want to do, right? So let's do the following initially. We will, suppose we think of, let's assign numbers. Let's call E as 1 and N as minus 1. Okay, so every time you go east, you think of it as a 1 and north as a minus 1, right? So you, instead of easts and norths, let's replace the string by 1s and minus 1s, and then the thing says that all partial sums are positive, right? All partial sums are greater than equal to 0. That's basically what it says. So let's do it that way, so that we can also see the other.
Last time I defined partial.
You define thing for partial sums, absolutely. So that's basically what we want to do. So the first thing here, I want to do this 1 minus 1 so that you can demonstrate the use of this other thing called map. Okay, so it's another function which acts on lists called map. So again, a very similar thing to filter in some ways. It has the following syntax. You take a function f, it's called map of f comma list. What it will do is it will apply this function f to every element of the list and produce a new list. Okay, so again an extremely useful thing. You want to take the entire thing sort of the en masse and just apply a function to every element. Okay, so let's map, so again we need a helper function which will do this, right? So let's define f to be the following function. What does it do? If x equals e, return 1, else, I guess something wrong, sorry, return 1, else return minus 1. Okay, so that's my function, and now I will use this function to convert my steps into steps of zeros and ones. Okay, so let's call it ZSteps. Z for 0 equals, what is it? It's a map. I apply this function f to self.steps, thereby converting it to ones and zeros. So for now, let's just check that this is working the way we would expect it to. Let's return ZSteps. Exec file. Lattice path, something, push this up. Okay, and let's just say, what did I say, L dot is dike. So for now I'm just returning the lists of ones and minus ones. So we've seen that the map guy is doing what it's supposed to do. All the n's have been mapped to minus ones, all the e's have been mapped to ones. Okay, so it's
trick for shortening f. You can turn a boolean into an integer. True becomes 1 and false becomes 0. So you can just say return int brackets x equals e.
But then I want minus 1, right? So then I should do some jugglery with that. It's not too bad, I guess. 2 times that 2 into that minus 1. Yeah.
Maybe that's too clever.
Yeah, I guess we always have to balance cleverness with readability somehow. So, readability by oneself some months down the lines. Okay, so ZSteps is just ones and minus ones. And now what we want to do is find partial sums, right? So this is something which Amri did last time, which I've already forgotten how you did it, but what do we want? We want all subsequences, sums of all subsequences, right? So Python already has a sum function. So it'll take a list and give you the sum of the list. So let's just apply sum to all the slices. So recall this slice business from Carl Dieter, which the following notation, sorry, I should say ZSteps. So slice A colon B will give you everything from index A to index B minus 1 in a list. So if I want initial subsequences, I'll just slice it. I don't need to say the initial thing, just defaults to 0, and the end is I plus 1. Okay, so ZSteps colon I plus 1 will just give you all entries, all entries from 0 to I, right. So I need to run through all values of I need to compute this sum, and I need to find the minimum of this guy, right. Okay, so let's use a list comprehension for this. Let's create a list which basically has these, let's create a list of partial sums. That's what I want to do. Okay, so let me say that list of partial sums. I could say map, but no, you see partial sums is somewhat trickier, no? See, it's not element, it's not a function acting on each element of the list. It's sort of having to do sums a little bit at a time. So first time is create another list whose elements are subsequences, right, slices themselves, and then I need to take the sum, and then I can do map, you're right, but I need to do that first. So I might as well just do it all in one shot. So list of partial sums is the following. Let's do a list comprehension. So by which it's meant you sort of say what the elements of the list are, sort of like set builder notation, right. So I say I open bracket, I'm going to form a list. What are the elements of the list? It is just sum, so this is the element, so it is the sum of ZSteps of colon I plus 1. This is the entry that goes into the list, right, and then like we do, so for what is I in range of what? Length of ZSteps, right, which is the same as self dot length, I suppose. So I can just say self dot.
So there is a built-in method called accumulate.
What is this? Accumulate?
You take a list and you just say from iter tools import star.
Okay.
And you say accumulate.
Okay, so that's the other thing that is there. So iter tools seems to have a lot of add-on extra methods. Let's see, from iter tools import star. Okay, and what are you saying? So if I have a list to
import iter. We have to say import iter. Okay.
This is fine. And then L dot accumulate, or
accumulate.
Oh, it's a function.
Yeah.
Accumulate something around. Yeah, it says it's not defined. Is it a method or function?
It's in version 3.2.
Oh, okay, that's fine. But there might be some, if there is nothing in 2.7? Sums, I mean, again, partial sums are such a common need that maybe there is something.
Doesn't look like it.
I see, okay.
Sorry.
Okay, so, but this is something we could always do, I mean by hand. You just create all the slices and then you sum up the slices for I in range of self dot length. So that's a list of partial sums.
That's not efficient. You're summing the same thing again and again.
You're right.
It's better to just loop over the list and then
Correct.
keep appending the.
Yeah, you're right, yes. Yeah, this is very inefficient. It just looks clever though. Yeah, you're right. So this is probably a bad thing to do in general. So maybe one should just say.
Oh, there's something called reduce.
Yes, reduce will do this, but reduce and sum. So but then again, see, you can't. You have to apply reduce to the slices, That's the same thing as this.
Reduce gives one thing, right? It
Finally gives you one thing. But so for example, between sum and, you see, you can always say reduce of add, comma, whatever.
and that is sum.
But sum is apparently better.
Yeah.
It's it's still more built in, whatever that means.
So maybe best thing to do is to
Just
iterate
loop.
over
Yeah, you're right. I guess one should just iterate. There's no sense in just adding the same things again and again, right? So for I, let's do this. So for I in ZSteps, what should one do? Do I really care about, I'm only going to worry finally if it's a Dyke path or not, right? I don't even need to figure out what the individual things are. Maybe I could just check it directly, right? I could just check it directly. Meaning, if
while computing the sum.
why don't we just do it like that? So we'll say, great. So maybe this is a good place to demonstrate. Okay, so here's one thing we could do, which is sort of slick, but maybe very inefficient. So let's do it a different way. Let's actually loop over the entire thing. So for I in ZSteps, let me compute the sum. So if let me say the sort of the partial sum at each point. Partial sum is 0. What should I do? Partial sum plus equals just I, right? Because I is already in ZSteps.
Oh yeah.
So the partial sum at each point is just I add that entry I, and if the partial sum is negative at any point, how should one do this? If partial sum is negative, if I say return, it will just exit the.
Yeah, but you're done. Right?
You're done. Yes. So it will just exit the thing at that point, right?
So colon. Then
Oh, sorry. Yeah. Return false. It's capital F or?
yeah. And then go back.
And then that's all there is to it, I guess, right? And then you can just say return true.
No, you need to check if the endpoint x and y are the same. You say if and
Yes, you're right.
if self.
No, that's the same thing as saying that the last entry is 0
Yeah, you can do that without calling.
without calling it again, right? So we need to check for one further thing, that the endpoint is 0. I mean, the endpoint is on the diagonal. So finally it should also say
PS equals 0.
yes. If PS equals 0, return true, else return false again.
Return true, yeah. Correct. So that's rather neat, yeah.
Okay, just think. Now, so if it is less than 0, then we are surely false. Return false. It goes all the way, then you return true. Okay, so let's do it one further way. So if P is equal 0, then you return true,
Yeah, else return.
right? So else return false.
Or I guess you could just say return PS equal to 0.
Exactly. Return P is equal to 0. Absolutely. That's what you would want to do at that point. Correct. Okay, let's do that.
No, just leave a space. You don't need to.
Sorry, I keep forgetting this. Return P is equal to 0, right? Okay. Yeah. Fine. That sounds good. Right? So this is the this is something which will tell you whether it is a Dyke path or not. Just check this. Execute. Lattice path. This is not even the same number of. So it start with an east, so that it will be a lattice path. East 1, 2, 3, 4 easts. Let's do that. oops, okay, L dot,
It's alternating.
oh it is, okay. Okay, at least this is correct. So L dot is dike. Let's just check that. Is true. It stays below the.
Try changing.
Let's put one more n here and compensate it by an e there. That's false. Right? Okay.
And the last paper, whether they are equal or add one more n.
Huh.
Oh, that
That will fail the other one, right? We should do it in such a way it doesn't fail. Let's do the other one. En. Let's add an extra e. That should do. Yes. Okay. So it's working fine, right? So we have checked if something's a dike path or not. And okay. So the let's see what else might one want to do. Dike path. Okay. So the other thing which one can do with an arbitrary lattice path is to sort of reverse the path. So you sort of start at the origin and end up somewhere, but you could just imagine doing just the same sequence of steps but done in reverse. So let's say the path ended up at A comma B. What's happening to that? Tab. Something wrong here.
Do you still want dike path or you want?
No, arbitrary lattice path. So I just want to take an arbitrary lattice path and figure out, and from it generate the guy which is.
So you have south and west or?
No, okay. Sorry, I should have said this and reflect. Meaning, so imagine doing the same thing, sort of like turning the paper over. Right? You imagine that that's the origin, and now when you go whatever east, you still go east essentially. You just read it in the reverse order, right? So that's one thing, but okay, that's just reverse, but there is also reverse and reflect, by which is meant every time. So okay, the point is if you just read this in reverse order, it does not preserve dike paths. Okay? So let's just check that. So if you take, so let's say you stay under the, so let's see what operation will preserve the property of being dike. So you have this, so I go east, north, east, east, north, north, for example, right? So if I read this in reverse, so it's like saying, okay, I start here, think of this, I mean the same sequence, so I have east, north, east, east, north, north. Now imagine doing the same thing, what's the reverse guy is north, north, east, east, northeast, right? But that's not a dike path anymore, because you start out with north, north. You're sort of going up anyway, so it's not under the origin. So I want to do this, but then I also want to reflect, by which is meant I not only want to read the word in reverse, but I want to swap the n's and the e's. So if I have an n, I will think of it as an e now. So I'll also swap e's and n's, e, n, n, e, n. Okay, and that guy will be a dike path. Okay. It's sort of easy to see if you think of it as turning the paper over. So you are now imagining that this is really the origin, right? I mean your axes are like this now. You are sitting here and this is now your new y-axis and you have the x-axis here. So it's really the same path but thought of as starting from the origin and moving this way. So if the original path is under the diagonal, this new path is over the diagonal. So you will sort of have to reflect it about the y equals x line in order to get something that's under the diagonal, that stays under the diagonal. So I want to do the following operation. I want to reverse and reflect. So I want to take this guy, I want to reverse the path but also reflect it. So I'll call it def reverse and reflect to self. So it involves two things. One, to take this list of steps and think of it in reverse, and then you want to change all e's and n's, right? I want to do two things. So let's just look at the first thing. How do you reverse a list? right. So again there are, as you can imagine, there are methods which will do this for you. So there are 2 of them. So for example, let's just work it out here. If I have 1, 2, 3, so I can do the following. I can say L dot reverse. Something's wrong.
You just type L again. It doesn't return anything, it just reverses.
Sorry, type L again, absolutely. Right, it's something which acts on L and just reverses it in place. Okay, but then L is changed now, right? It just changes it in place. Now, if you don't quite want to do this, you can apply something called reversed. So let's call it P equals, but now it's a function reversed of L. Okay, now remember L is 3 to 1. Something's wrong. List of P. Right, it returns an iterator. So this is like sort and sorted. I guess there is a similar thing for sort. So if I have, say, a list consisting of 2, 4, 3, if I say L dot sort and then see what it does, it sorted it in place, right? But let's say it's the same thing. I don't want to do that. I don't want to change my original list. Then what you will want to do, so there are situations where you will need each of these. So now if I say P is sorted of L and see what P is, here it actually is the list, not an iterator. Okay, so here P sorted just gives you a new list, which is the the original entries in sorted order. Okay, so here we want to do reversed. We want to apply this reversed function, get a sort of you get an iterator for the guys in the reverse order, but then you also want to do this swapping function. You want to apply this map to it. The map is the swap map. So let's define this helper function, swap north and east. So what does it do? Takes x, sorry, so I don't know, if x is e, return n, and vice versa. X is e, return n, else, sorry, what?
Quotation.
Else colon return e. It's fine, right? Okay. So this is just a swap function which we will use to apply this map. So what should we do? We need to do the following things. We first apply the reversed guy to self.steps. It will now create the list, or rather an iterator for the list of things in reverse, and then you apply the map function to it. Okay, so you say map of this guy, and to which you apply swap any. I suppose this will work with an iterator as well, not with the actual list.
There's something called IMAP.
I see. Okay, so let me just check this out here. So if I take
but I think map will work with an iterator. It's just that IMAP will return an iterator. It's map will return a list.
Will return a list, right?
Yeah.
Okay, fine. Okay, so suppose we define a function f is lambda x going to 2 times x. So I want to see what happens if I map f comma L. So it has done this, but now I want to see, let's do the reversed business. So P is reversed of L. So it's as we saw, it was an iterator. Now let's try and apply map to P. Seems okay.
It returns a list, not an iterator.
Returns a list.
With IMAP it will return an iterator.
Iterator, but then the input needs to be an iterator as well.
No, I think it probably
Even if it's a
doesn't,
list. I see. Okay.
I think.
Okay. So there's somebody says something called IMAP, which is probably also useful in many situations. You might want to only get a iterator for the answer, not the answer itself as a list. But here it's what we want. So you return not return, sorry, reverse and reflect of self. So what is it supposed to return? So what have I done? So this is the new set of steps, right? So these are the new steps. It's the list of steps for the reversed and reflected path is this. But what should this guy return?
It should return the big path, the lattice path associated.
Absolutely, it should return the lattice path which has this as initial data, right? So I want to return an object of class lattice path again. So I return lattice path of something initialized with these guys, right? So this is the usual thing we will want to do. Okay, so reverse and reflect will give you this. So let's see, let's run this again. Close. Should have just done it myself. Now let's say L is, let's give something that is known to be like path. So lattice path of, so let's just do what we were doing, E, E, N, E, E, N, N. It sounds like another N, right? One more N is in order. Okay, let's see, is it a like path? Is like, okay. Okay, it's true, right? And now we want to see what happens. So L dot reverse and reflect gives you a new, supposed to give you a new path. Let's call it P is this. Now, as we just said, P should also be a like path. So let's just check. So P is again an object of the same class. It's also true, right? It's not the same path. There are 3 E's for a start. Okay, so it's just operation of reverse and reflect, which preserves the subset of like paths here. Okay, so let's see, what did I want to say? So there are, okay, so great. So maybe some space for homework. It's only 10 minutes. So firstly, think of other methods that you might want to implement for like paths. Okay, so the one obvious one is concatenation. If I have two, not like paths, but all lattice paths. If I give you 2 lattice paths, you will want to define a concatenation, right? But here let's so try and do it by something that Madhavan mentioned, which is by using this magic function mul. So imagine, try and overload this multiplication operator, whatever it's called. So try and define a mul method, okay, which will do the following. It will take this guy and another lattice path and then create the fellow which is the concatenation of these 2 fellows, right? So it's kind of easy to see what you will want to do here. You just want to take the steps of self and the steps of L and you will concatenate these 2 things together. So we already talked about a list method called extend, which will take one list and another and sort of concatenate them. So you concatenate the steps, form a new list of steps, and you create a lattice path object with that as initial condition. That will give you the mul operation. Now the advantage of doing this is now you can just give commands like L star P. So you create 2 lattice paths L and P, and then you can just say L star P on the thing, and it will just compute their concatenation, right? Because you have defined it using this special function called mul. So that's concatenation is one operation. The other interesting thing is, so this is one homework exercise, define mul. The other is to define, so for now I'll just say pass, define another method called to partition in a box. Okay, so what is this? What does this mean? A lattice path can actually be thought of as, there is a partition somehow hiding behind this. So you think of, so you have a lattice path, so it starts at the origin, it ends at some point a comma b. So it always stays within this box, right? Because you're only allowed to take a and b steps. You cannot go beyond the box whose length is, whose 2 sides are a and b. And so the point is, if you do this, imagine you have, this is really a lattice path. Then there's one of 2 partitions involved. There's either, so it forms a Young diagram shape, right? So if you trace, the path itself is nothing but the boundary of this shape, the Young diagram. So you can actually, these 2 things are equivalent. You can either think of it as a lattice path or as a partition, a Young diagram which fits into an A cross B box. Okay, these two notions are identical. You can define this obvious bijection between them. Given a path, you think of the shape whose boundary is that path, or given a shape, you take the path which is just the boundary of the shape. Okay, so the method you now want is to convert to this other representation. Given a path, given a lattice path, find the partition in a box. So when I say def 2 partition in a box, what I want to do is give you a lattice path L and say L dot 2 partition in a box. The output should be a returns the partition corresponding to the lattice path, given lattice path. So that's what this method should do. Okay. So I guess these are 2 homework exercises. So in just the remaining 5 minutes, since I was sort of talking about these various looping and list and so on, I just want to talk about something called zip and enumerate. I have something there. So I just have a file here. So there's this another useful thing which allows you to sort of loop through lists. So for example, let's assume we have 2 lists. So A is 1, 2, 5, 4, B is say 9, 10, let's say it has another element 2. Okay, so A and B are lists, not necessarily of the same length, but often they are generated in the same situation for some if you are trying to model some mathematical object, and you might want to sort of go pair by pair. You will want the first elements of A and B, second elements of A and B, and so on, and you will want to run through them. Okay. So there is this thing called zip in Python which does the following. If I give it 2 lists A and B, zip of A comma B generates a new list, okay, and whose entries are tuples, and as you can imagine, it only runs as far as the minimum of the lengths of the 2 lists. So if one or the other list has extra elements, they are thrown out, but as long as they have the same number of elements, it works. So now this actually works with many more. You can have this, and you can do zip of A comma B comma C, which will give you tuples. So you can use zip with any number of lists. What it will do is it will run as far as the minimum of the lengths of all those lists and give you tuples of those guys. Okay. So this is often a useful thing because now you can run through this. You can say for I in zip of A, B, C, which means your I will now run through these tuples, and then you can do something with those tuples. So that's one called zip. The other is enumerate, which sort of does the following. So I had my list A. Now if I say enumerate of A, so often you want to do the following. So I just call it something P equals enumerate of A. So let's see what P is. So enumerate is the following. If you have a list, you want to generate tuples which are I comma A of I. Okay. So let me just list. So what it now does is it again does something like zip. It generates tuples, but with the tuples look like index comma the value at that index. Okay, again potentially a useful thing because you might want to somehow keep these pieces of information together. Right? Not only the index, not only the element of the list, but also which index, which position it occurred at. So if you want to do that, then enumerate is another useful function which is already there in Python. And so sometimes this so sort of an interesting thing with zip is if you remember the thing that Amri talked about last time about unpacking arguments to functions and so on. Okay, so let's just take this example. I have zip of ABC, which we'll call D. D is zip of ABC that we already created. So D is this list of tuples. Now if you unpacked the arguments of D, so D is a list, each of whose entries is already a list in some sense, it's a tuple, right? So if you unpack the arguments, so what does unpacking the arguments of D mean? I guess it makes, what does unpacking do in this case?
It makes a tuple, it unpacks. You can assign them to different.
Right, so each of them becomes a separate, right. So each of these 3 things here.
So you can say x, y, z equals star of 1 and 1.
Star,
X, y,
right.
z equals star of
191. Okay. So for example, if you do star, but no, I guess it won't work. No, only to functions. I think if you just do it on the,
Yeah, it doesn't work.
it doesn't, only if you're passing it to a function. Okay. But here's the thing, if I did star of D, right, what it's sort of doing in the background is it's creating three separate entities. One is the list or the tuple 191, another is 210.2 and another is 523. Okay. So these are now three different guys. Think of them as three different lists again. Suppose I did a zip to them again. Okay. So I have 191, 210.2 and 523, three lists which I now zip again. Right. What does zip now do? It's supposed to take it, column by column. So it will now do 1, 2, 5, 9, 10, 2 and 1, 2, 3. Right. So here's the thing, if I did zip of star, zip of star D really, so zip so what did it do? A, B and C, so they were of different sizes unfortunately. So if I made them equal sizes, right, if I did, so what's just too muddled here, sorry, let's make it simple. So I have A is say 1, 2, 3, B is 4, 5, 6, C is 7, 8, 9. So zipping them is like reading them along the columns, right? That's what zip does, right? Unpacking them is like reading them, row by row. Okay. So if I zip them, so I have D is zip of A, B, C. Then what it's now doing is it's reading it along the columns, right? 1, 4, 7, 2, 5, 8 and 3, 6, 9 have now become the columns. And so if I sort of did this again, if I zipped, so I unpack D and I zip it. Okay. If you unpack D, it now thinks of it as three separate guys which I now read column wise. What you get is the original fellows again. So observe that these are the three original guys A, B and C. Okay. So this is sort of a somewhat maybe esoteric thing, but just pointed to how zip and star work. So this is basically what it says. So zip, star, zip is identity. It's an involution in some sense. If you do zip twice, you apply zip to the unpacked zip version of something, you get back what you started with because of the way it does it. So one of them is reading along columns, the other is reading along rows, and so at the end of the day it's back to where you started. Okay. It's transpose, exactly. Just applying one zip is transpose, as we are just saying, right? This is the A, B, C, 1, 2, 3, 4, 5, 6, 7, 8, 9 are along the rows. Zip is transpose really, it's reading along the columns. Right? Now unpacking it is again, what are you doing? You're thinking of these guys arranging the columns as the rows essentially, right? You apply transpose and you apply transpose again. You apply another zip is like doing transpose again. So it's like saying you apply transpose twice, you get back to where you started. Okay, but it's a good thing to know that zip is like transpose in some sense. Maybe that's a quick way of remembering how it works. But again, it's something that's potentially very useful when you're trying to loop. You might want to say, go through these various things and, in various ways. So here's another homework problem in addition to the ones that we already said about lattice paths is, create something which will take, 3 or 4 lists and splice them. So by splice we mean, so you put, for example here you put the first entry of the first guy, the second entry, reading along the columns in this way. So the spliced version of this list would be 1, 4, 7, 2, 5, 8, 3, 6, 9. Okay, so you just put the various entries one after the other. So a spliced, you take three lists and sort of splice them together to get one single list. So in some sense it's like further unpacking what we are calling D there. So there's, by the way, what does double star do, Amri? Okay, because you said something about double star in your thing, right?
I did.
Or no, single star or double star, something you were saying.
Single star.
Okay, fine. I guess there is no such thing as double star. Okay, fine. So that's maybe it.